Okay, so this is a project joined with a lot of people that are all the names down there. Taisuke, among others, who's here. And what we've been doing is, well, starting, I guess all of you here are familiar with the whole reproducibility crisis and how lab experiments in psychology and economics don't seem to replicate. And what we've been thinking about with this project is how can we estimate and predict reproducibility, in the sense that we want to run replications, but it's often replications are often very expensive. We need larger sample sizes, for example, and we need some kind of structure to decide which replications to run and which not to run, and how are we going to select those in a formal way that's not driven by other incentives that we don't want. So we've been thinking about this for a while, and in the paper that came out in Science in the spring, we ran 18 replications of 18 lab experiments in economics. And what we also did was that we let experts trade in a prediction market to trade on the replication probabilities of all these papers. And the idea about for that was that maybe we can get a good estimate of people's beliefs about replication, and maybe that's a way to help us maybe decide which replications to run, but also just to see how well people predict reproducibility. And we're doing the same thing now in a new project with 22 studies from Science and Nature that were published in recent years, and we're also running a prediction market on that. So basically, this paper is just following along that line of reasoning, but taking it one step further, saying maybe we can do this. We don't need experts. What if we just have an algorithm? How well can an algorithm predict replication? So just to summarize what I'm doing, I have a data set of a lot of replications, and each observation is a pair of an original study and a replication of that study, right? So using that, I predict the outcome of these replications. And importantly, this is all about correlations. There is no causality, we can't talk about how these features, how we can change p-value to increase reproducibility or whatever. I guess you're all on with that point. So the two main questions then are, how well does the most accurate model predict replication, and how does that compare to these estimates that we got from prediction markets? And also, what can we say about the features that we use and which ones are important? And interestingly, it turns out that the model that I build is capable of predicting 83% of replications correctly, which, if you compare to the outcome of the two prediction markets, is much better, actually. And also, there is explanatory power in all kinds of variables, not only in the ones that we maybe would expect, like p-value. So for this discussion, I thought we could talk a little bit about, well, if you think that these methods are sound for doing this, mainly maybe the two second parts, which are about, do you have any other ideas of features or things that we should include in a model like this? And also, how would you go about implementing this and using it? I think that's the most important question to talk about. So the data comes from these four replication projects. They, all in all, encompass 144 studies and replications of those. And out of those, 130 are complete so that they can be used in the model. 55 replicate, 75 don't replicate. And out of those 130, we have data on prediction market prices for 55. Yeah?
When you say replicate or don't, how are you?
Next slide.
Oh.
So because of how we traded, how the prediction market worked, we needed a very simple replication outcome variable. And you could, there is a lot of things to say about this. It's very crude, of course. But basically, we assign a replication to be successful whenever the p-value is below 0.05 and the effect goes in the same direction as the original study. And this is the kind of notion of replication that the market was trading on. This has tons of problems, but in the appendix, I don't think we'll have time for that today, but I also use relative effect size as an outcome variable, which is much harder to predict because it's a continuous variable, but maybe it has more information too. So these are the features that are included in the model. There is both like features from the original paper and features from the replication. The idea about that is one way you can use the model is to think about if you specify a specific replication, then you would know like what country you're going to run it in, who is going to run it. You'll plan a sample size. So those things are known ex ante. So maybe that's something you would want to include in the model. However, I also get results if you remove everything from the right column and just look at an arbitrary replication and how is the model able to predict that. So yeah, there's things here, the like fundamental features of the statistical test that we're testing, but also things like which discipline it is. Those are only social psychology, cognitive psychology, and economics. Compensation, like if it's course credit or cash. Effect type, interaction effect, main effect, correlation, that kind of categorical variable. And here, this is really difficult to see, but this is the correlation. So up there is replicated, which is the main outcome variable that the model uses. And you can see that it's correlated with the original p-value and, of course, the replication p-value. So it's too small to see much on this slide, unfortunately. But the main point, I guess, is that there isn't that much clear correlation structure. There are correlations here, but it's not like super obvious what's going to happen. So it's all the variables, and so it's correlations. The blue diagonal is like 1 because every variable is perfectly correlated with itself. And so it's the same variables on the x and y axis. So I think it's like the 7th line would be, the 8th line is the 7th line is the variable replicated, which is the outcome variable of the model. Going forward to how I do this, I don't know how familiar you are with basic machine learning approaches, but please ask if you don't understand something. But the first thing to do is to split the data set into a training set and a test set, and then not look at the test set at all. So the test set, I just leave it, 23 of the randomly selected observations to make sure that the classes are even. I leave them out and I don't look at them. And then these 107 observations, those are the ones that are used in the model. So on those observations, I use what's called cross-validation to train the model on 9/10 of the data and test it on the 10th part of the data. Do that over and over again to get an estimate of how well a specific model is doing. And having done that, I can compare different models and select the one that's the best. Is that all right? You following? And it turns out, which perhaps one could predict looking at the correlation structure, that one of these classification tree models, random forest, which is often successful in situations where you don't really know much about the data and you don't have a specific model in mind, is the best. So that's a model where it's a black box model because you have all these, you pool a lot of decision trees, and each decision tree would be assigning a probability to each of these two classes, replicated or not replicated, and then you take the average of 1,000 of those trees, and that gives you the model. So a problem with this is that you can't really understand what's going on under the hood. So you end up with this ROC curve, which is a way to measure performance in when you have a two-class situation, a binary outcome model. On the x-axis here is the true negative rate, which is the probability that like the accuracy of the model at predicting the failed replications. And on the y-axis is the true positive rate, the probability, the accuracy of the model in predicting successful replications. So the ROC curve is a curve, each model has one of these curves here, that gives you the trade-off between successfully predicting a successful replication and successfully predicting a failed replication. For example, a perfect model would always predict with 100% probability that a specific replication would be successful or not. And a perfect model would have a 90-degree line going all the way up to 1 and all the way over there. Because such a model, no matter where you decide to have the probability cutoff, it would always have an accuracy of 100%. That doesn't happen, of course. Instead, we have models that, depending on where, like, maybe the model isn't completely sure about the outcome of a specific replication, so it assigns a probability of replicating at 60%. And then we have to decide what to do with that. So we have to decide if 60% is enough to say that, to assign a successful replication to that. So what you can see here, those dots, for example, 0.37 for the random forest model, that's at the level at which the line is closest to the top left corner. In other words, the cutoff level at which the model has the best accuracy. So using that cutoff level, I can then look at the test set and see how well the model performs. If you say that whenever the probability of replicating is larger than 37%, we assign a successful replication. And whenever it's below 37%, we assign a failed replication. So doing that with these 23 observations, this is the result. So it says that 83% of the cases it gets the results correct. And also the AUC here is a cutoff independent metric. So if you go back to this slide, the AUC would be the area that the model covers. So it's the area under the curve. And that's I guess a more, it's a better metric of how well the model performs, but it's a little bit more difficult to understand. So in this case, the model has an AUC of 86, or 0.86. And interestingly, as I was talking about before, if we want to look at what happens if we remove all these replication features and think of an independent model that doesn't specify the reproducibility of a specific project, we still get an AUC that's pretty high. And also, one question that we've discussed a lot and that comes up when I talk about this is how much of this is because social psychology papers don't replicate. So one way of thinking about that is what happens if we remove this dummy for disciplines, and it turns out that while the accuracy drops a little bit, it doesn't have a big impact, which I think is interesting because maybe one takeaway from that could be that there is the things that make social psychology a good predictor for failed replication, they're captured by things that are already in the model. So it's also correlated with things like small samples, for example. And that's kind of nice because, yeah, and maybe predicted as well, I don't know. Furthermore, if we remove, if we just look at basic features, features like the p-value, the effect size, and things like that, that are very, that one would expect are the most important, those definitely decrease the accuracy. So there is something in this modeling approach that helps us, it seems. Any questions about this? Yeah?
So one of the underlying themes between beats and the broken science is that this problem of lack of replication is common across areas. So I was wondering, instead of having 23 observations, why not add the other 100 from the Gnostic study and then?
Oh, those are in here. So those are in the training set. So the data is first, it's trained on these. So, I mean, these are all the 130 observations that I use. And the reason why it's only tested on 23 is because if you don't do it like that, you have the problem of overfitting. So if you train the model on the whole data set, then you could just as well be fitting a line between the points, and like you couldn't really say anything about accuracy that's trustworthy, I think.
So why didn't you test like using cross-validation over like 120 something and then chopping some pieces and like moving the?
Because of the same reason, I guess. So cross-validation would get you a little bit further, like it solves most of the problems with overfitting, but you still wouldn't have a complete, like doing it like this, you get a very, like the model hasn't seen the data in the test set at all. So it's a clean way of thinking about accuracy.
For another way, it's why do you do this just one time? Why don't you get a distribution of these AECs by drawing redrawing the test sample 1,000 times and replicating what you've done 1,000 times to essentially get a distribution?
I guess for the same reason, then if I do any model selection after that, I would be probably overfitting to the data, right?
Well, I'm just saying to reproduce exactly what you did, but just do it 1,000 times to get a
Mm-hmm.
distribution.
And don't use information
And-
across withdrawals.
Yeah.
Pretend you didn't see
Yeah.
the data and redo it to know
That way you're not dependent on what the training sample turned out in that first draw was, right?
So you mean like cross-validation of the cross-validation? Nested, basically.
Yeah. Well, yeah. Okay. I mean, I wasn't going quite. I'm just saying that you can essentially bootstrap out
Sure.
an AEC.
Sure, I haven't been doing that because I was worried about overfitting, and but maybe now that the model is sort of finished and I won't be collecting more data and things, maybe this is a good point to get some confidence intervals and stuff here. Yeah.
Earlier this year, the Statistical Association put out this statement saying that paying so much attention to P.05 was causing a lot of problems with the reliability of the literature and urged people to stop paying so much attention to it. So if people actually figure out a way to stop paying so much attention to P.05 world, what happens to these models that are being built?
I guess you could use something else. I mean, as a dependent variable, as I also do in the appendix, and it's right now that model is not very good, probably because it's a continuous variable. But you're right. I mean, this is built in the sense in the context that we are in right now, and I guess this is just a first step. Maybe you can. The more data we have, the better models you can build too, I guess.
So do you think the word replication should include, or failure to replicate should include sample size effects? Because I would have thought we would be dealing with sort of subtle contextual issues that you thought you were doing the same experiment, but you really weren't.
Mm-hmm.
The change of sample size produces a completely predictable outcome. And I wouldn't say you failed to replicate because you had a sample size that was very different from the other one. I mean, you could use that word if you want to, but it seems like you should have a word that would distinguish between two settings that are statistically indiscernible, but maybe have different sample sizes, and two settings in which the results are distinctly different and not compatible with sample variability.
Yeah, this is a question that often comes up, and I mean it is difficult to distinguish a direct replication from a conceptual replication, and how is what is external validity, and like I'm not sure how maybe we need better words for describing what's happening here. I agree with that.
What Ed was asking, let me just ask one thing. It's related to both of these points, which is another, maybe I misunderstood that, but you know, there's a test. You guys have this in your science paper of whether you can reject the null of equal effects across the original and the replicated study, which is related to the sample size issue. If you do a replication with 10 units, it's so underpowered. That test is really underpowered.
Yeah, of course.
Rather than your continuous effect size as an alternative measure, I would have thought that sort of rejecting equal effects across the original and replicated study would be like the most natural metric of replication or failure to replicate. And so that might be, and that gets away from the p equals 0.05, but it's a well-defined test.
I agree. Yeah, right now I've just been using one continuous and one binary, and the reason why we chose this binary is because of how we used it in the markets. But I agree, that could be a different model to test. To see if the effects are like statistically, like the original effect size is, if the replication effect size is within the confidence interval of the original effect size.
Or if you can't reject the quality.
Yeah, exactly. So comparing this to, it's hard to say something about the prediction market results because the sample size is so small. I'm hoping to get data from a third prediction market study to get a larger sample size here, but right now if I build the same model on and train it on this data set and test it on this tiny data set, it seems like it's not doing very well, but I don't know. I wouldn't assign too much value to these results, I guess. Yeah. Of course. Yes, we write very careful like replication reports to say exactly what we're going to do, how big the sample sizes will be. They also get access to the original papers, and it's incentivized with real money. So whatever the money the traders earn, they keep. Sure. Yeah, thanks. I'll...
1 or 2 more minutes.
Yeah. Oh, really?
Yeah.
So the Lasso result, like if you just want to look at what predictors are important, this is a kind of funny result. I mean, the Lasso is a regularization method, so it shrinks all coefficients that are correlated down to 0, and then it keeps the ones that are most orthogonal. So these are the 3 coefficients that are still in the model. Kind of easy to predict, maybe. And yeah, so since we're out of time, I guess we'll just, this is the same for the random forest, but here without signs because you don't know it. These are the conclusions, and maybe we can just talk. Yeah, these are the points for discussion that I wrote down. But maybe the most important thing is like, how do we use this? How can we use this, I guess? Does anyone have any comments about that? I would love to hear it. Or any other questions for that matter. Sorry? Yeah. Okay.
Great.
Thank you.
Thanks.